still, well, a good example of what happens to the converse, well, what happens to the concept of the converse when we realize that really not every statement has a converse to begin with, because not every statement has the if-then statement on one hand. On the other hand, frequently you could transform that statement into an if-then statement, an implication, and then it has a converse of some kind. Okay, so and that is a good example. We had already example without the converse. In fact, well, this one has if. What was the statement that without the converse? Well, this one in blue. For every x plus 1 is positive. For every positive x plus 1 is positive. There is no then. Okay, so there is no converse. But you could restate it, as you can see below, in the form of a implication that there is a converse. So that's a trivial example, but this is Fermat's theorem, so it's a big deal. And the question about converse might appear, so you have to actually make sense of it. If anything, if there's a possibility of to state it in different ways, then you might try to find the converse, then decide whether it's true or not, which we did, and then if not, then still not the end of the story. So let's take a look at it again. So I have my Fermat's theorem stated up there. If C is a local maximum or minimum, an extreme point of a function, and function is differentiable at that point. Okay, at that point, then the derivative is equal to 0 at that point. Okay, so it is an if-then statement. So you can the most plain way to do it is right there. For every f, for every c, I have two conditions. C is a local maximum minimum of f, and f is differentiable at that point. And the implication is that f prime is 0. Okay, so then the question was, what's the converse? And we realized that it doesn't make a lot of sense, because certainly f prime of z is equal to 0. It already includes the condition of differentiability. So you can't really say that derivative equal to 0 means that there is a derivative. It's just not really an implication. But so that we can deal with that. We have to deal with that. But a bigger calculus point here is that it doesn't have to be neither maximum nor minimum. And the example is once again x cubed, derivative equal to 0, but not the it's not an extreme point. Okay, so once you realize that and you say that it is simply not, well, that's what I did in the next line. So once again, converse in the next line. So I took differentiability out. You see right here, I took differentiability out of our implication, and so then it would be no turning. It will then relate it to the whole business of reversing the arrow. Okay, so then we have derivative equal to 0, the local maximum minimum, and that is the question is addressed in calculus 1. The answer is here that the answer is no. It doesn't have to be extreme point. X cubed is the example, counterexample of to the converse, which means that it's not true. Okay. And is at the end of the story. Frequently, yeah, we got to do something about eating.
Oh, sorry.
So the converse is not true. That's not the end of the story, though. And because you have there's such a thing as a partial converse. And the partial converse means that the B statement over here does not imply A. Okay, that's what we just discovered, or discovered in calculus 1. But what if we strengthen B? How can we strengthen B so that the implication would become true? So changing as much as possible, which don't change anything else. But we just strengthen B. And the answer is, once again, from calculus 1, and that is the second derivative. not equal to 0. So in other words, how do we get rid of x cubed as a counterexample? So how do we exclude it, preserving as many as possible of our other applications? The case is x cubed has 0 derivative, second derivative. It is an inflection point. You can see it right there, in inflection point. The second derivative changes the sign. So let's exclude that. Then the function will have to behave in a more straightforward way. So the concavity will have to be preserved. So it has to be either this or that. Okay. So that's helpful. So that is the extra condition that we add to our to part B to statement B, that the whole thing becomes then correct. So let me state that. So as I called it, a partial converse So once again, I go the same. The beginning it doesn't change for any f, for any c. Here I ask f, in order to accommodate the implication itself, I will have to require f to be twice differentiable, so that we have two derivatives available. And then I will, I have the same, it doesn't quite fit, but f prime of c is equal to 0, f double prime of c is not equal to 0. Okay? And then the implication goes back. C is a local maximum minimum of f. Okay, so we did manage to reverse the error. We found the error first. There was, we rearranged things so that little by little, so that at least the statement would make sense to begin with. The converse would make sense. We discovered that even though it makes sense, it's not true. And then we tweak a little bit of the statement so that we would create a new theory that is true. So in other words, we have now two theorems. So make no mistake, we have one theorem, and then what is partial converse of Fermat's theorem. That's what we're talking about. And so that you might have to explore. So every statement or definition comes with a lot of questions that you have to ask about it and investigate before even you try to do any application. So as you can see, I have been talking about calculus a little bit, and there is nothing nothing about differentiation or integration. So that big part of calculus is kind of pushed aside if you start looking at mathematics as mathematics rather than just kind of manipulation of symbols and applications possibly. You look at it for its own value. You have to, so it has to make sense. It has to make sense, and this is how you make sense of things. So you have a statement. You explore the strength of the statement to begin with. That is another issue that we're going to consider. So if A implies B, do we really need A to be as strong as it is in order to imply B? Okay, so we already had an example when we tried to do converse, and B was not strong enough to imply A, so we strengthened it. Okay, but you can also go in the opposite direction and try to look at your implication and ask yourself, are all of these statements necessary? So maybe I can. So these are the conditions. I'm talking about part A now, A and B. Can we weaken the conditions, part A, in order, and then B still true? Okay, so that's once again routinely done in mathematics. And I mean, when you study calculus, then somebody already had done that job for you. So they, as much as possible, all the statements are as strong as they can possibly be. Or at least the way they can be presented. Sometimes the corners are cut in order for simplicity. For simplicity, sometimes such a strengthening is ignored. Well, maybe I'm thinking about an example. Well, the example that I had here. So once again, is the blue here. X positive, then x plus 1 is positive. Of course, it's true to begin with, but if you want to really think about it as a theorem, then the next positive is the condition is just too strong in order to x positive, x plus 1 is positive. All right, but I could, that's A, this is B, okay? So how about I weaken A? X larger than 1/2, then x plus 1 is larger, I'm sorry, if that's strengthening. Weakening, larger than negative 1/2. Then x plus 1 is still positive. That's what I mean. Okay, so if you could do something like that, you probably should, as far as mathematics is concerned. Similarly, if you can strengthen B, that's also good. So, for example, I could say x positive. Can I strengthen B? Then the original one, x plus 1 larger than 0. A similar statement, but stronger. X plus 1 larger than 1/2. How about that? Okay, so it's already better. So also happens that's how you try to sort of push the knowledge forward, right? So based nothing on but just thinking about possibilities. So we'll do that as much as possible in the future. So there will be one more couple of theorems I want to look at calculus. I just had a question about yesterday. Well, not from calculus. I'm just wondering if you're paying attention. So do you know what the orthocenter is?
The what?
Orthocenter of a triangle.
Heard of it.
What?
Never heard of that.
No?
No.
Oh, that's okay. It's not important, really. No, really. So there's a definition, orthocenter.
Has nothing to do with orthogonal, does it?
It does. Orthogonality. It is actually the intersection of all three heights.
Okay.
That's ortho. There it comes from.
Okay.
Heights are perpendicular,
Yeah,
right?
yeah, yeah.
So is the intersection of the three heights of the triangle. Well, so once again, that doesn't matter. It's just an example. So height, oops, and another height. Well, and then there are several ways to do something like that. So it kind of looks like it's in the center, right? So and then to attach words to it. There's circumcenter. There's another kind of center. I can't even remember. The only point why I bring it up is just to ask what's next. You see the definition. What do you do?
You prove the definition?
No, there's nothing to prove about the definition. The question that you're supposed to ask about the definition, somebody gives it to you, and maybe they have done their job, or maybe they haven't. So what is the question that you're going to be asking about? So think as a mathematician. You're building a geometry as a theory, which is supposed to work and be totally rock solid, and you have to everything has to be ironed out, and build brick by brick or layer by layer. So you're going to be building a whole theory based on this. So maybe it's some kind of important point, and it might tell you something about the triangles, but the good policy is to ask certain questions about it. So we talked about that yesterday. Well, remember what we talked about yesterday, the definition of the limit, and we ask certain questions about it. Right off the bat, not later on, but we defined it, and before we start computing limits, let's be sure that what we're talking about makes sense. There is basically one question to be asked. So.
Is there any counterexamples?
Okay, so you're moving in the right direction. So, but specifically counterexamples of what? Well, what were the questions we asked about the limit? It is, okay, so that's could be start. Is it, so the big question is this well defined? Definition well defined, okay? And then the number one could be, is it unique? Is it unique? Is it unique?
Seems pretty unique.
Yes, it does. Can you justify it?
Justify why, I mean, those lines are only going to intersect at one point.
That's right. So two lines, unless they're parallel, they intersect by one point. So well, there you go. It cannot be two. Okay, so that's very transparent. There's the second question. Which did not come up as much with the limit. What was the other question? They always come in pairs, existence and uniqueness. So you could go start with uniqueness. We did it with limit as uniqueness because the existence was obviously not satisfied. We knew that it's possible for a sequence not to have limits. Okay, so we moved on to the uniqueness in order to be able to use the words the limit. Okay, so this is different. So uniqueness is obvious. What is it? Does it exist, or does it always exist?
I would assume so.
Well, you can. I know that you want to assume it. You want to believe what is given to you that is true, but you have to be. I mean, it's a little beyond you. Well, what if you were going to repeat that story to somebody, and then you have to make sure that everything is solid.
I mean, every triangle has a height, or it's not.
It has three heights.
Yeah, three heights. Yes.
Yeah, and then that picture is very convincing, isn't it?
I think it's convincing.
It is, but it is a misleading picture. It is exactly the misleading picture. If you jump from the definition to the picture, then you won't be questioning it.
Yeah.
But think about it. All you have is three lines.
Yeah.
And two lines intersect. What about three? What can happen?
You can have two intersections,
Well,
three intersections.
Oh.
pairwise. We are speaking of three lines intersecting at one point, which is an exception, not a rule. Look at those. I drew three random lines, and I ended up with no one single intersection. So it is quite possible that there is nothing. And so that is actually, the answer is still yes, but, and so the whole thing does make sense, but that is actually an actual theorem. So that if you start proving your theorem, you would actually not start with that pretty picture. Try to prove that existence starting with that picture. The picture already assumes that there is a single point.
Yeah.
Okay, so you have to take that picture and draw a picture that you know is wrong. So you would draw it like this. You would make sure that they do not intersect.
Yeah.
Okay, and then show that that's not the case. So that's the challenge of you ignoring your intuition, something like this. Well, maybe I can do a better job here. Like this. Okay? So then, you know these are not 90 degrees, but you say that they are, and then you work your way from here.
Okay.
And then somehow demonstrate that that triangle is actually not a triangle, but a point. Okay, so that's a challenge, and that is a theorem.
Wait,
It
so
might.
are you always going to have this orthocenter, or is that triangle?
The theorem says that, yes, always.
Oh, so that triangle that you made the second time is just like a made-up one, but like that won't happen? Or?
No, well, once you prove that it always exists, then you can use it for further constructions.
Okay.
Just as good an example is the circumcenter. The circumcenter is the center of the circle that circumscribes the triangle. Okay, so it's also been in a similar way. After all, you can have three heights, you can have three medians, and you can have three bisectrics. And once again, the question, every time you can say, well, let's take the point where they all three intersect and call it some fancy name. Okay, and every time you have the same question that maybe they don't intersect. Okay, but the circumcenter, if you think about it, it's actually, everybody knows that you can circumscribe a circle around a triangle, and but it's not obvious that it is, so it has to be proven. But this one is especially good illustration of what might trip you up, things such as assumptions and pictures. Pictures are dangerous in mathematics. So you might plot it. If imagine that I was not drawing it by hand, but I was forced to actually draw it in a literal sense with some kind of software. So straight lines, right angles, I draw it, and then they would have to intersect the first picture. Okay, so then how are you supposed to prove with that? Yeah, so you have to, I don't know. Well, anyway, so that was just an example and a reminder, and we'll every time we will be introducing a few things in this course that you haven't seen before. So after doing a little bit more of calculus, we will turn into other things that you may have not seen before. And every time we have a definition, we have to deal with these two. Is it well defined? And it is two parts: uniqueness and existence and uniqueness. Usually in the order of existence and uniqueness, but it depends on the circumstances. Okay, so we have taken care of Fermat's theorem. I want to take another look at a couple of more theorems. The next one is Rolle's theorem. You remember that one?
Sounds familiar.
Okay. Okay, so what it might be about? Any idea?
The slope of that line, there's a point on that curve.
Yeah.
The slope of that line, the slope of the tangent is equal to the slope of the line between the points.
Right, so which actually happens to be horizontal. So the way you state it, it's called the mean value theorem, which follows from Rolle's theorem. Rolle's theorem is simpler, but it actually sufficient for our purposes. So once again, we have a graph which starts and ends at the same level, horizontal level. In fact, let's say on the x-axis, and then the conclusion that we make is that there is somewhere a horizontal tangent somewhere like this. Okay, so in horizontal tangent, or in other words, the derivative equal to 0. So let me first of all I'll do it the way everybody remembers, and which is the punchline, which comes at the end of the theorem. And so I'm writing it the wrong way, but that's just, I don't want to start. I want to write what we do remember and then add things that are missing. So the conclusion is then there is a C such that the tangent is 0, or we prefer to use the derivative for that, so a derivative is equal to 0. Okay, so that's the punchline. That is then. Where is if? Remember any conditions? There are 3. One is, well, let's start with the one that's on the picture. Well, I put it as number 3. So what?
If it starts and ends at the same.
Right. So there's an interval, and f of a is equal to f of b, and in fact, probably, let's say it's equal to 0. Okay. So that's condition number 3 that we see in the picture. But we need to make sure that what we've got makes sense. So, what conditions are missing?
Has to be continuous.
Continuous, yes. Why do you want continuity? What?
That's it, so between A and B.
C is between A and B. I will put it here in AB. Okay, that's fine. That's the missing part. Okay. So continuity. Wouldn't you want differentiability more than continuity? Well, because we have the derivative, so we need differentiability. So condition 2 is actually differentiability. So f is differentiable, but where?
Between A and B.
Can you be more precise?
Everywhere between A and B.
Well, the point is,
C?
we have to exclude the endpoints. That requires, why do I exclude the endpoints, if you remember? Because differentiability requires the function to be defined in an open interval around that point, okay? Which means that I cannot speak of differentiability at point A unless the function f is defined beyond a to the left. So, and we assume that it's not defined. Okay, same, I cannot go beyond b. We cannot discuss differentiability there unless it's defined. So I defined on the whole neighborhood. On one hand, on the other hand, we are well, and then there's first condition is continuity. And why do we care about continuity? Well, you remember the relation between differentiability and continuity?
It can't be differentiable if it's not continuous.
Right. So in other words, that's a contrapositive, and the contrapositive of your statement is what? If it's differentiable, then it's continuous. Okay, which means that it might be strange because we're talking about differentiability already. Why would we say continuity? Well, the point is they're going to be continuous on the whole interval.
Wait, that's not the converse?
No, contrapositive.
Okay.
No, right. So direct statement without negations is it's differentiable, then it's continuous. Converse, if it's not continuous, it's not differentiable. Yeah.
Okay.
Okay. So I want a continuity here, but that would be pointless because differentiability implies continuity because I already have differentiability of f and therefore continuity at every point between a and b. But I will include a and b. So. Well, you can see that why does it matter? Why that condition 1? I only added 2 points. 2 points continuity at the endpoints of the interval. That in addition, condition 1 only adds so little to the condition 2, and yet if I don't add it, you can demonstrate that the theorem is not true. So imagine that I have condition 2 and 3, and I don't have condition 1. Then you should be able to have a counterexample.
Condition 3 wouldn't hold true?
Condition 3 is fine. So condition 2 and 3 are satisfied. So
I'm just
that's
saying, if condition 1 wasn't there,
right.
then condition 3 could be false.
What I'm saying is that the conclusion of the theorem does not have to hold. This is what I would ask you to demonstrate. So just condition 2 and 3, no 1. Why? Then the conclusion does not follow. So something about the picture does not have to be satisfied. Well, just think about continuity. What continuity means, it means that points are attached to each other. And so it's a continuous curve, literally, that the point A is attached to the rest of the graph, and the point P is attached to the rest of the graph. Once you remove condition 1, they don't have to anymore. So imagine point A and B are where they are, remain still on the x-axis, but the rest of the graph could be anywhere. Okay, so imagine that. So now, what would make that graph necessarily have a horizontal tangent? So I have A and B over here still. So these are points on the graph. Well, let me mark them as points on the graph. Points on the graph, and here's I'm plotting the rest of the graph. So these are the 2 points. The graph is located in between. Okay, like this. Okay, so differentiable, continuous, everything at the endpoints, starting and ending is the same. differentiable, all that it's here, but it's not, there is no horizontal tangent line anywhere. Okay, so all the conditions are necessary. Once again, it is the trying to strengthen the theorem as much as possible so that there would be no, no, like building a house so that those brick or stones, especially building pyramids in such a way that there is no light in between. So you cannot, everybody who comes after you will say, well, I would like to improve on this, but I cannot. Okay, so it's perfect as it is. Okay, so that's roughly what this theorem is. It's hard to make any stronger. You cannot, you can strengthen the theorem by either, so if this is A and this is B, you can either weaken A or you can strengthen B. Okay, so we cannot, and as far as I can tell, we cannot weaken A, or strengthen B as far as, at least nothing comes to mind right now. So the only way to strengthen is the whole thing, strengthen the whole thing. Well, actually kind of weaken both A and B, and you have more general theorem, which is the mean value theorem. Okay, so same story as above, only it is sloped, and so you're not talking about necessarily a horizontal tangent. Anyway, so the logic is really straightforward, right? So well, but let me do it anyway with the quantifiers. So once again, if you will be thinking about converse, and I don't really see a chance for a converse here, but so once again, it will be for any f, right? So for any f. Now, once again, you have to be reasonable here and try to think of the preamble, may make it as large, but not too large. So I think I will add condition 1 and 2 as the preamble. Differentiability continuity, that's usually how you do it. You limit, if you have your f function or number, whatever, you say as much as you can about that number if of what kind of class it is. So class continuity, class differentiability, so you'd rather have them of that taken care of before you get to the implication. So I'll say f is continuous, so I take the two conditions on AB, and f is differentiable on AB closed. Okay, so that's my preamble, and then the conclusion will be the rest. So let me go to the rest, and then the condition 3 will be the hypothesis. Okay, so so I could have just the way I did it on the right. The whole thing is condition A, 3 conditions is A, and the conclusion is B. That certainly is a valid way to put it, but if you want to just tweak it a little, this might be a better idea. Okay, so then f of A is equal to f of B is equal to 0. That actually, the one way to strengthen is throughout 0. It doesn't matter, right? It doesn't matter on what level it is. Okay, so just as well, let me throw it out. Okay, so the endpoint, the beginning is the same, and then I conclude what? The res. C in AB with f prime of C is equal to 0. Another way to strengthen is to, you can actually claim that C lies exactly between A and B. As long as you make sure that A is larger than B. A is less than B. So actually that probably should appear before. For any A, B, A less than B. Well, doesn't fit. Okay, so sometimes obvious things actually have to still be added if you want to strictly write everything that's available. So for every A, for every B, condition is A less than B. So I want the intro to be of length. That is actually it is actually a mistake not to say that A is less than B. That is a mistake. Because if you have only one point interval, that the whole theorem falls apart. So for any A, for any B, A less than B, for any function f, under the condition that's continuous here, differentiable there, then if the endpoints, the value of the function at the endpoints are satisfied, then there is a c within the interval where the derivative is equal to 0. Okay, so that would be the statement. Okay, so just a few words about the proof. It's certainly that the homework for you to look at the proof and try to figure it out and sort it out. It could be long, could be short, depending on the circumstances. But if it is short, it's probably one might be skipping over things. But by short, I mean you can actually say it in like two lines of text. But it's proofs tend to be short, but dense. And then to actually understand them, you have to unwrap them. Okay, so that's my restatement, more formal restatement of the theorem. Okay, so proof. Any ideas about the proof? So, but forget about that. Last picture at the top. Why would such a point exist? Well, first of all, you can certainly see why it could be true. Imagine geometrically take the horizontal line and shift it, and there is a highest point. At some point, it will have to touch the graph, right? Touch the graph, and that's the definition of tangent. Tangent. That's what tangent means. It means literally means touching. And so if I translate that vertical line like this, so I have a horizontal line like this. So I start with this line, the x-axis pretty much, and then start shifting it like this. And at some point, it will touch it. So that is the idea, but that you certainly can convince yourself it's true. But we hear about talking about more formal things and how to actually come up with justification of this. So remember, every proof will have two parts at least, or maybe more. But it always either uses the definition or uses theorems. So we have two things. We have continuity, we have differentiability. And I just want to ask you one. And we had the theorem. That is the theorem that will be helpful, right? So local maximum, if you have a local maximum minimum, then the derivative is equal to 0. And that's what we want to conclude. So the connection should be made right there. So we want to use Fermat's theorem because the conclusion of Fermat's theorem coincides with ours. Okay? So the only thing that remains, look at it, the conditions are also satisfied as long as we do it right. The conclusion will be that the derivative is equal to 0. So the only thing then, when you see the connection and you see the tool you want to use, you have to demonstrate the condition A is satisfied. So then you have to show that there is a local maximum minimum point, a minimum point or maximum point within interval AB, local one. So I don't want to go into all the definitions, but well, I just want you to see that how things are developing. So the idea then is idea number one, I suppose, use Fermat's theorem. Okay, because it concludes that derivative is equal to 0. So that will be the ending of the proof. But then you work your way backwards, because now you have to justify why the condition of Fermat's theorem is satisfied. Why is there must be a local maximum minimum. Okay, so the theorem is not like the theorem is in number theory we've done, where you can actually construct things. You can show what it is either by formula or by computation or algorithm that we know ends. Here it is a pure existence proof, so we know that something exists, because if it doesn't, then we have a contradiction. So in other words, we can only use theorems for that. So idea number two, and there is idea number two here. I wonder if you just remember what would justify this. So why there is a local maximum minimum.
Any continuous line between 2 points that are same elevation?
the last one is the right one. So you're talking about the continuous function. It will have a maximum or minimum on a closed bounded interval. So if we have interval AB, there will be that picture shows that it's true. There will be always a highest point, and there will be always the lowest point. So you don't have to get to before you get to start talking about derivatives. If you have a function, as long as it's continuous on some interval AB, right, there will be always the highest point, and there will be always the lowest point. Okay. So, well, if anybody remembers the name of this theorem, I'll just call it the extreme value theorem. Okay, so another theorem from calculus. So as you can see, once again, we're not doing any computations with derivative or integrals, but this is the actual meaty mathematical part of calculus are these theorems that actually create the foundation for everything that follows. So extreme value theorem demonstrates that there is a highest point. It is actually about the global maximum minimum point, so you have to work your way from global to local somehow. So that still remains an issue because, secondly, why is it an issue? Because you see the point on the right, the highest point is actually at the end point. And what do we know about the end points? The problem with the end point. It's not differentiable, right? So we cannot use that point on the right, unfortunately. So that's trouble. So there's a trick. There's a clever trick that is easy to overlook. Well, just take a look. We'll talk more about that next time. So, yeah, I will assign the homework. I will assign the online homework later today. Okay, so I wanna we'll probably come back to calculus again, but I think we have a taste of what's going on there, and certainly the Rolle's theorem is one of those theorems that really have everything coming up together. You can see that the little theorem and proof is short, but a few things come in, such as two theorems that are valuable on their own. They come in to prove this one. So we'll probably get another look at it. I want to restart the number theory again. So once again, number theory, but on a different level. Well, actually, it's not. Well, maybe it's actually not number theory, but well, there's no. They're just saying numbers. Then we'll see where we go from here. So I want to go to something very beginning we started with, and that is the the word is parity actually. The word that stands for odd versus even. Okay, so just a convenient word, parity. So what's the parity of the number? It's either odd or it is even. Okay, so and then the algebra of these is we had it. Remember, even plus even is even. Odd plus even is odd. Odd plus odd is even. Okay, so this is a very short, this abbreviated statement of the theorems that we have, and some of them we actually prove it. So, but you should be able to certainly prove all of these on your own. The theorem, like I said, an odd number added to an odd number is an even number, like that. But we are going past that, and we want to actually understand what this says. What is that? It seems that we can say when adding an even number to an even number, you can say it, but actually these equations make sense even if we just understand what even stands for. And what even stands for is, in a way, the set of all even numbers. Okay, so even, what it stands for, the set of all even numbers. And same for odd. Okay, so in other words, we're not talking about numbers one at a time, but rather what we did, we took our reals, no, I'm sorry, not reals, but rather the integers, and we split it into two. So we have 0, 2, 4. These are the evens, and then we have the odds. -1, 1, 3. Okay, so odd. So this is the way we understand these numbers. Then what we have is this is a partition. Remember that, of Z. Why? Because partition means that it is representing a set as a union of two sets that have no intersection. In other words, they are disjoint. You don't have any numbers that are simultaneously odd and even, and there are no numbers that do not belong to it. So if I, well, let's call them a P and Q. So just for convenience, P and Q. So Z is equal to P union Q on one hand. So there are no, every integer is either one or the other. But secondly, P intersection Q is empty. Okay, so that's a partition. But so this is about sets. So we split it into two and then fine. So the set situation is very simple. It is described right here. But we're not interested in sets only anymore. We're doing algebra. So, but algebra this time, it's not algebra of numbers anymore. Like I said, I want to actually do algebra on the whole sets of on the whole set of even numbers on one hand and the whole set of odd numbers on the other. Okay, so the better way to, if you do algebra, we actually did it. We rename the time. Okay, just a minute. So we rename P and Q. You remember what we renamed them based on that little table over there? Odd and even. We're going to be talking in terms of remainders. So odd and even, it's what it stands for is whether or not the number is divisible by 2. So an even number divided by 2 is an integer, so a remainder is 0. Okay, so even means remainder is 0. Odd means remainder is 1. That's the remainder theorem. Remember, every number will have can be divided by another number with the remainder that lies between 0 and less than the divisor. So there are only two options, 0 or 1. So that's why we call even 0 and we call odd numbers 1. And so that algebra that we have, I have in the corner over there, makes more sense. 0 plus 0 is equal to 0. 1 plus 0 is equal to 1. 0 plus 1 is equal to 1, and 1 plus 1 is equal to 0. So this is the algebra of those two sets. So those sets can be treated algebraically as if they were numbers, and that's what we're going to pursue. It's very simple algebra. I mean, there are only two numbers to worry about, and only two operations, only one operation so far, and that's the whole, like, addition table. Okay, so we'll continue with this, and we'll look at the multiplication table.